Welcome back. So probably one of the most important uses of linear approximation is differentials. When we first started talk about derivatives, we said that the change in y over the change in x becomes dy dx when we want the change in x and the change in y to become very, very small. In other words, going from the average rate of change to the instantaneous rate of change. dy can be considered a very small change in y. dx can be considered a very small change in x. So if y was x squared, y prime would be 2x. dy dx would be 2x. We could use that function to find a very small change in y, given a very small change in x. If it's written in function notation, f of x equals x squared, f prime of x equals 2x gives us the same thing, that derivative. So a new look at dy dx. So dy is the rise of the tangent line relative to the change in x, dx. A change in y, so delta y is a change in y that occurs relative to change in x, delta x, dx. So we're looking at the change in y being dy and the change in x being dx. And that's essentially the slope formula, right? Unless we look at a very small change, right, where we can look at the instantaneous rate of change, where we're going to stay as close as we can to that point of tangency. Because notice, the further away we get from that point of tangency, the worse of an approximation we get. Look how far apart this and this is, right? So we want to stay close, right, to our point of tangency, because then our tangent line, our linear approximation method is a very good model for estimating. So a new look at dy dx. We know that the change in y over the change in x, which is the average rate of change, approximates f prime of x, the instantaneous rate of change. Right, so then change in y, delta y, change in y, is, so now notice, notice our formula there. So change in y, delta y over delta x, right, change in x, is approximately f prime of x. What if we multiplied both sides by the change in x? Notice we'd have change in y, which is dy, is equal to f prime of x times change in x. In other words, a change in y is equal to the derivative times a small change in x. Recall that dy dx is not a quotient. It's the notation for the derivative. However, sometimes it's useful to use dy and dx as actual quantities, and this is one of those. We are going to be looking for change in y's given small changes in x. How much will y change? So if x changes too much, it's not very accurate approximation because we are too far away from the line. Right? And a lot of this is in your notes, but if anything is not, just add that to your notes. So we want to stay as close as possible, right, to our point of tangency. We want a small change in x. Otherwise, who wants a not a very accurate approximation method? All right, so here we have our function, y equals f of x, and we have some point, a, f of a. Right? And so if we stay close to a, if that dx is pretty small, right, then the value of the tangent line is very close to the value of the function. If we start to get too far away though from a, notice that the linear approximation is not such a good approximating method if we're too far away from that point of tangency. So we're going to be looking for how is dy changing given small changes in x. So geometrically, the differential dy is exactly the change in the linearization of f when x equals a changes by a small amount. So how much is y changing, the value of the function changing, right, when we change x by a small amount? And that is our linear approximation formula. Right? And so notice here, and that linear approximation for dy can be found by taking the derivative times the change in x. Right? And that's what we're going to be using to calculate out the change in y. Right? So it's another use of our linear approximation method, but specifically we're not looking to evaluate a function at a certain value. We're not approximating a value of a function. We're approximating a change in y. All right, so the differential of y, consider change in y over change in x is equal to f prime of x, which is dy dx. All right, so then we can say dy is equal to f prime of x times dx, which is our change in x. So we are looking to find a change in y given a small change in x. The things that we're going to know, we're going to be able to calculate out a derivative, and we're going to know the change in x. So this is called the differential of y. The notation is df of x, or dy, is equal to f prime of x times dx. It is an approximation of the actual change of y for a small change of x. And let's look at an example. Or actually, no, sorry, I have a few more things, and then I have an example. So if y equals f of x is a differentiable real function in some interval, and dx is a small change of the independent variable, then the differential dy gives us the change in y for a small change in x. And it is found, so that change in y is found by taking the derivative and multiplying it by dx, the small change in x. The variable dy is always a dependent variable, depending on both x and dx. If dx is given a specific value and x is a particular number in the domain of the function, then the numerical value of dy is determined by taking that value of the derivative times the change in x. Its use is, right, an equation to find the change in y, or a numerical value for dy. So we can either have an equation to find the change in y if we're not given dx, or we can have a numerical value for dy. We can find out how much is dy changing. And we'll do both. We'll mostly find how much. Right? This first one, we're just going to find an equation, right, that we can use to find the change in y if someone gives us a change in x. Right, so here we want to compute the differential of y equals cosine of the square root of x. Right, so we're going to be finding an equation to find dy given x. Right, so the very first thing we're going to do is we're going to find the derivative. Right, so, and then since it's written in y, I'm going to write it dy dx. So dy dx equals, all right, so this one's going to be a chain rule, right? So the derivative of cosine blop is negative sine blop times the derivative of the blop, right? And instead of writing square root of x, I'll write x to the 1/2. Right, so that's going to be negative sine square root of x times 1/2 x to the negative 1/2. Let's simplify that. Dy dx equals negative. Let's put the 2 in the x in front because that looks terrible behind. So this would be actually let's put the sine square root of x in the numerator, and then the 2 square root of x in the denominator. There we go. So we'll simplify it all at once. Dy dx equals negative sine square root of x over 2 square roots of x. The differential, the equation to find a small change in y, given a small change in x, is going to be the value of that derivative, sine square root of x divided by 2 square roots of x, times the change in x. Right? And that's all there is to the equation for the differential. So this equation can be used to determine approximate change in y dy given an x value and a change in x. To approximate the change in x dx given a desired change in y dy and an x value. Right? So if we know how much we want our dy to change, we can look and see how much dx has to change. Right? And a lot of these problems will be real-world examples, right? So you'll have some context to these change in y's and change in x's. But this one here was just to write the equation. On the next one, we'll actually calculate the numerical differential. So what is a differential? It's an approximation of the actual change of y for a small change of x. And that is all it is. Now here, up above, I have the actual change in y. All right. So the for f of x equals x cubed plus 2x minus 4, find the exact change of f if x goes from 1 to 1.01, then the approximate change in f if x goes from 1 to 1.01. Well, the exact change is just a plug and chug. All right, so it is, we just substituted and evaluated. So I found f of 1.01 minus f of 1. That's all I did. I plugged in the values. How exciting, right? And so the change in y would be 0.0503. That's how y will change given that we change x from 1 to 1.01. All right, and you can look over that and say, yep, she's plugged it in. All right, now let's use a linear approximation method and see how close we get. All right, so first thing I need to find is the derivative. F prime of x equals 3x squared plus 2. All right, so now our differential dy is going to be the 3x squared. Actually, let me put this in parentheses. 3x squared plus 2, because we're going to take that value and multiply that by the change in x, or dx. There's the equation to calculate it out. Now let's actually calculate it out because we have the values. All right, so we have dy equals, all right, so when we're plugging it in, we're plugging in the 1. The 1 is what's going to go into our equation, not the 1.01. That's our change in x. All right, so our x that we're plugging in is going to be 1. The value, our change in x, we're increasing, right? So 1/100th. All right, so that's going to be our change. All right, so we're increasing x, so we're obviously going to increase dy a little bit. All right, so now let's just plug everything in. So we've got 3 times 1 squared plus 2 times 1 over 100. All right, so that's going to be, 5 over 100. I guess I should have made it in terms of a decimal, shouldn't I? Because that one's as a decimal. That's okay. We can easily make that back to a decimal. So that's going to be 0.05. I don't know about you, but that was less work. And I'm close enough. I think 0.05 is close enough. All right, matter of fact, it took to the 4th decimal place before we saw any differences. So how much will y change if we change x from 1 to 1.01? It's going to change 0.05. All right, so when you're doing these ones, the value your value that you plug in is your starting value. Because we're not using a nice value to calculate out another value. We've got a starting value, and now we want to change x. And so change in x is going to be the difference between the new value and the starting value. And also you can think of a little logical reasoning, right? If I am increasing x, I kind of expect y to increase. Maybe not always. I guess maybe it depends on the function, but it's kind of a way to think of it. All right, so now let's look at this one. All right, so we have a function is defined implicitly by the equation x squared y minus 2y cubed equals 3x cubed minus 4. Approximate the change in y at the point 1, 1 as x changes from 1 to 1.01. Right, so now when we go to plug it back in, we have we have an x and a y because there's an x and a y in the equation. This is our starting. This will give us our change in x, right? So the change in x is going to be 1.01 minus 1, or 0.01, which is the same as 1/100th. It'll probably be easier to keep it as 1/100th. All right, so now first of all, let's find the derivative. All right, so this one is, we've got product rules, we've got implicit differentiation. Let's take care of that x squared y. All right, so if u is x squared, then du is 2x. If v is y, then dv is dy. All right, so that's the only product rule we have. So that's going to be the first, x squared, times the derivative of the second, which is dy, plus the second, y, times the derivative of the first. I'm going to write the du first, because that just looks nicer. 2xy. All right, and then minus, all right, the derivative of 2y cubed would be 6y squared dy dx equals, derivative of 3x cubed would be 9x squared, and the derivative of the negative 4 is 0. We need everything with dy dx is on one side. It makes sense to just move, and then everything else without dy dx is on the other. It makes sense to move the 2xy. So that gives us x squared dy minus 6y squared dy dx. Oops. Did we? Oh, sorry. There we go. Dy dx. Forgot my x. I don't know what happened there. And then equals 9x squared minus 2xy. We'll factor out the dy dx. And we've got x squared minus 6y squared equals 9x squared minus 2xy. And then divide both sides by the x squared minus 6y squared. That gives us 9x squared minus 2xy divided by x squared minus 6y squared. To get the equation for the differential, it'll be dy equals 9x squared minus 2xy over x squared minus 6y squared times dx. Now what we have to do to find the change in y is plug in 1 for x, 1 for y, and then times 1 over 100 for 1/100th for the dx. And we've got it. I'm going to switch colors just because it's kind of busy up here. All right, so our change in y is 9 times 1 squared minus 2 times 1 over 1 squared minus 6 times 1 squared times 1 over 100. And now you can find out how much will y change if we change x by 100th. Right, now this is not the exact change, but it's a very close approximation. So let's see, that's going to be 9 minus 2, so that's 7. And that's going to be 1 minus 6, so that's negative 5. All right, so here we'll decrease a little bit. dy is equal to negative 7/500ths. So that's how much y will change if x increases by 0.01. Right? And that's all there is to it. Let's try another one. All right, so here's our real world problem. Suppose 1 inch of a cube is known to be 14 centimeters long to within 0.3 of a centimeter. Estimate the possible error in the volume of the cube. All right, so here now we do need to write an equation. It's not given to us. However, all you have to know is how to find the volume of a cube, right, which is just x cubed, where x is the length of the edge. All right, so we have only one variable when it comes to a cube, and that's the length of the edge. And if you cube it, you get the volume. So we're going to take the, and I already have a lot of this up. Actually, this is all up here. Nothing for me to write. All right, so take the derivative as a related rate. We take the derivative of x cubed. That's going to be 3x squared. So dv dx would be 3x squared. right? And then to get the linear approximation model, we move that dx. So dv, the change in volume, is equal to 3x squared, the derivative, times the change in x. All right, so our change in x is given to us within 0.3 of a centimeter. That's our change in x. 14 is the value of x, right? That's what our starting value is, right? So what happens? How much will the volume change? If we change the side length by just 0.3 of a centimeter, well, we're going to change the volume by 176.4 centimeters cubed, right? So a little change in x here is going to lead to a lot of change in volume, right? If it's really, really important, right, that we don't have too much change in our volume, then it's going to be really, really important that we're pretty close to our starting value. All right, so the 14 here is this is the starting value. And this 0.3 is our change in x. All right, so this one I didn't write up here. All right, so now we want to estimate the change in the area of a square when its length is decreased from 10 inches to 9.8 inches. All right, so let S equal the length of the cube. The function, let's call it A. A would equal the side squared. This is a square. Take the derivative as a related rate, so dA ds, oh, that should be an S now. dA ds would be 2s. And now to make this derivative be a differential, all you have to do is move that ds over. So dA equals 2s ds. And now we can calculate out how much will area change if we decrease the side length by 0.2. All right, so we have, and I'm going to write this ds as negative. So if it's negative 2 over 10, that's the same as negative 1/5. I think that'll be easier on the calculating. All right, so we always substitute our value. So the change in area will be 2. Our S is 10. It's the starting value. So that would be 2 times 10 times negative 1/5. That's going to be pretty easy to calculate out. So the change in area would be 4 inches squared. Oops, excuse me. Negative 4 inches squared. So the area of the square is going to decrease by 4 inches if we decrease the side length by 0.2 of an inch. Consider a circle of radius 10. If the radius increases by 0.1, approximately how much will the area change? All right, so r is the length of the radius. The formula for the radius of a circle is pi r squared. We're going to take the derivative as a related rate. All right, so we have A equals pi r squared. So dA dr, right, the change in area relative to the change in the radius is going to be our dA dr, our r derivative, is going to be 2 pi r. To make changes from a derivative to a differential, just move the r over. So dA equals 2 pi r dr, and we can use that to determine the change in area given a small change in radius. And remember, of course, this is approximating, right? We are using the tangent line, so the less we change, the smaller the change in x, the better the approximation. All right, so I'm going to just write that in as 1/10. So that is our dr, and 10 is our r because that's our starting value. Let me move this down a little bit. So dA equals 2 pi times 10 times 1/10. So the change in area will be 2 pi, what is this, inches, centimeters? It doesn't say. All right, so 2 pi. We won't put units. Units squared 2 pi units squared. That's how much our circle will change, right, if we increase it by 1/10 of it, the radius by 1/10 of an inch, approximately. All right, compute dy and change in y if y equals cosine x squared plus 1 minus x, as x changes from x equals 2 to x equals 2.03. All right, so our function is pretty much defined for us, is cosine x squared plus 1 minus x. All right, there's nothing really to do with defining the variable in the function. It's already given to us. Take the derivative as a related rate. So dy dx equals, all right, so it's going to be the derivative of cosine is negative sine blob, whatever's in the blob, times the derivative of the blob. And then the derivative of the x is just 1, right? So let's clean this up. dy dx equals negative sine x squared plus 1. And the derivative of the blob of the x squared plus 1 is going to be 2x. Now that looks terrible because then it's like, where's that 2x go? Are we taking the sine of that? I don't know. So let's move that in front so it's very clear that it's negative 2x sine x squared plus 1. All right, so now we can substitute 2 for x. That's our starting value. We are increasing, so this is oh, sorry, it says dx. And that's the same as, I'm going to change that to 3/100ths. Make it a fraction. All right, so excuse me, we were almost finished. Here's our derivative. Our differential is dy, so this is the differential. Here, I'll put it on the other side. dy equals negative 2x sine x squared plus 1. So the first one here, this is the derivative. Used to find the slope of the tangent line. This is the differential. Used to find change in x. So used to find slope of tangent line. Used to approximate the change in y given the change in x. Important to know the difference. All right, so we have dy, the change in y, just the change in y. Change in y equals negative 2 times, 2, not 10. 10 was the last problem. 2 times 2 sine 2 squared plus 1. Well, this isn't going to be a pretty number. And then, oh, sorry, we forgot dx up here. And then dx. And the dx is 3/100ths. We'll simplify this as much as possible. It's not going to be much. Dy equals, so I've got negative 4 times 3. It's going to be negative 12. Sine 5. It'd be nice if it was sine 4. Sine 5. Actually, sine 4 pi would be nice. Sine 5 over 100. We could simplify that because the 12 and the 100 reduce. So we could get a decimal approximation, but we'll just leave it. You can plug it into a calculator if you wanted. That would reduce by 4, so it'd be negative 3 sine 5/25. That's how much it'll change if we plug that into a calculator. Okay. And I think this is going to be the last problem on this tape. A tuber is approximately spherical in shape. if the radius of the tumor changes from 14 millimeters to 16 millimeters, find the approximate change in volume. All right, so volume of a sphere is 4/3 pi r cubed. That's the formula for volume of a sphere. All right, so r is the radius. All right, our starting value is 14 millimeters. Our change in x, right, is going to be the new value, 16 minus 14. That's going to be 2 millimeters. So that's our change in x. So we're going to plug that in for, this should say dr. I have a tendency to keep writing dx. Right, and this should be r, but you know what I mean. All right, so let's, now that we've defined the equation that would represent a spherical tumor. All right, so let's take the derivative as a related rate. All right, so dv dr is 4/3, times 3, I forgot to write the 3 in, pi r squared, right? Just using the power rule. Those 3's will cancel. So this is dv dr equals 4 pi r squared. And now for this to be a differential, dv equals 4 pi r squared dr. All right, so now we can find how much will the size of this tumor change if the radius increases by 2 millimeters. This is something we should be worried about. So the increase in volume is going to be 4 times pi times 14 squared times 2. And that's going to be 196 times 2. So 196 times 8. It got dark in here. I have one light on, and as I move, it goes out. And unfortunately, this calculator is solar. So 8 times 196, 1568. So the change in the volume is 1568? 1568 pi millimeters cubed. Sounds like it might be something to be concerned about, doesn't it? All right, so thanks for joining me and looking at differentials to approximate a change in y given a change in x. All right, so bye for now.